class, we have just found out the equation for Biot-Savart law, or magnetic field due to a current carrying conductor. That was a straight wire, so the equation was very, the diagram was very simple. But now today we are going to find the magnetic field due to at the axis of a circular loop. Okay, at the axis of a circular loop. Now let us consider this to be a circular loop, and I flows in anti-clockwise direction. Remember that I is current which flows anti-clockwise. Okay, anti-clockwise direction. The length of the loop will be L. Total length of the loop over here is L. Now, what are we going to find is, we are going to find the effect of magnetic field at a point P. Now, at the axis. Axis means on the line of the loop. Okay, axis means over here, somewhere here. So, we are going to find the strength of the magnetic field at this point. Let us write this to be P. Okay, at this point P, we are going to find the strength of the magnetic field due to this circular wire which carries current which flows anti-clockwise. Now, using Biot-Savart law. Okay, so what I am going to do is, we will take a small portion over here, small portion that will be dl. If the length of this loop is L, small portion will be dl. Now let us see at this point what will be the direction of magnetic field. For that we will follow the rule, that is right hand thumb rule. Now according to right hand thumb rule, before that let me complete this diagram a bit. Okay. Let me take the radius. Okay, this is kind of an oval, but imagine this is, I have drawn this diagram like this. It is a loop which is kept this way, and the radius of this one is A. Okay, that small a. Distance from this to this point will consider to be x. Distance from this dl, okay, this point to P, this point P will be your distance between the point where the magnetic field is being generated and where it is being felt. That distance, you know, we have to consider it to be R. I wrote this part. This is R. This distance is R. Now, what will be the direction of the magnetic field at this point? Okay, this point is P. I just rubbed it because too much things will be seen over here. Now, if it moves this way, okay, if your loop is kept like this, if it moves this way, okay, the current is moving like this. Current is moving like this. Loop is kept like this. Okay, I have drawn it this way, but it's not possible to draw it this way. But imagine you have got a loop which is kept like this, and current is flowing like this. Current flows like this anti-clockwise. Okay, and making it flow anti-clockwise. At this point, what will be the direction of the current if current is flowing this way? Then the direction of the current, suppose if it's flowing like this, outwards from the board, then the direction of the current will be at this point. Direction of the magnetic field, will be like this. Okay, this is the direction of the magnetic field. Let us write D. Okay, direction of the magnetic field. One thing you need to remember is what we have discussed before was your current element dl and r. This is the distance between current element and magnetic field. This point is perpendicular. This is 90 degree always. Okay, this is 90 degree. So your dl is perpendicular to r. Now at this point also, the magnetic field and the current, if dl is perpendicular to r, what we know is where the current is flowing and where the magnetic field is generated. You always know that according to right hand thumb rule, if current is flowing upward, the magnetic field is perpendicular. Okay, it flows perpendicular. So this dB is also perpendicular to r. These three things are perpendicular to each other. You need to imagine those things. Okay, it's very crucial to imagine all these things. This r and dB is also perpendicular to each other, whereas dl and r is also perpendicular to each other. Now next, we'll take another point over here. This point will also be dl Okay, there over here the current is flowing like this. Okay, if this is outwards, the current over here is flowing inward. You take a look to check if the current is flowing inward, and the magnetic field over here is like this. Okay, the direction of the magnetic field is circular. It doesn't flow in a particular direction. It keeps on changing according to the place. So at this point, the direction of the magnetic field will be like this. These two are the direction of the magnetic field due to these two current element. Due to this dl, the magnetic field will be flowing this way, and due to this dl, the magnetic field will be flowing like this. Now, what you have to find is, you are going to find this current, this one, that is d. Now, for that what we do is, we extend this line further. Because your magnetic field is a vector quantity, it flows in a particular direction. These two vectors has to be resolved into two vectors. We have frequently done that, and you know how to do that also. These two will be resolved into perpendicular and a base vector, that is sine and cosine. So, let me draw two lines for this one, for this particular vector. I am drawing these two lines. Let me make it of the same color so that it will be easier for you to understand. Okay. For this dp, I am taking this chalk. Now for this vector, when we resolve two vectors, when you break two vectors, this dp can be made into perpendicular and one a base one. Okay? Now when we resolve this vector over here, this also will be resolved. One will be in the same direction as the previous one, and one will be the base one like this upward. Now, okay, so sorry, I haven't drawn this one. The distance between this dl and this point. Again, if this is a loop, so distance between this and this will be the same, that is r. Suppose we take this angle to be phi, this angle will also be phi. Now, what I have to do is to find this particular angle. This is a bit confusing, just listen carefully. For finding that particular angle, okay, suppose this angle is 90 degree. This angle is 90 degree, this is phi, so the remaining angle becomes 90 degree minus 90 minus phi. Okay, this is the angle over here. This angle, this small angle, this angle over here is 90 minus phi. Again, what we know is dB and dl perpendicular to each other. So this two angle will also be 90 degree. Okay, dB and r. Sorry, this r and this dB is also perpendicular to each other. So this angle is also 90 degree. So if this angle is 90 minus phi, the remaining angle over here becomes phi. Okay. Similarly, same thing if you apply it over here, this angle becomes phi. Okay, I'll just rub this so that you don't get confused later on. This angle and this angle is phi. I have told you how. If you haven't understood, you can just rewind the video and just listen carefully. Okay? This is 90 degree. If this is phi, the small angle over here, 90 minus phi. Again, this too is also 90 degree. If this is 90 minus phi, this becomes phi. Now we need to find the magnetic field due to this look at this point axis using Biot-Savart law. Now let me first write the equation of Biot-Savart law. Biot-Savart law is dB is equal to mu naught by 4 pi IDL sin theta divided by r square. This is Biot-Savart law. Now let us apply this in this diagram over here. Now what we know is, what is theta? Theta is the angle between dl and r. Always remember that theta is the angle between dl and r. What is the angle between dl and r? It is 90 degree. Sin 90 is 1. If you apply sin 90 1, then this equation becomes, okay, when you write sin 90, we becomes like this. Now, let me write this equation number 1. This is just for the small section of a loop. Now for the entire loop, for the whole loop. For the whole loop, what we do is we integrate that. We integrate. To find magnetic field B, we integrate dB. Is it only dB that we integrate? No, we integrate it with the angle that is phi. When we change this, when we change the position dl over here, this phi changes. When we change to different point, this phi keeps on changing according to the position of this dl. That means when we change the current element or the dl point over here, this phi keeps on changing. So your integration should be along sine of phi. Okay, integration should be along dB sine of phi, because it is a circular loop. Had it been a straight wire, we just have integrated dB. But because it is a circular one, it changes according the angle over here. This phi changes according to the position of the dl. So we have to integrate it along sine phi also. First of all, before doing this integration, let us find what is sine phi. Sine angle is perpendicular by hypotenuse. So if this is a phi, this is a triangle over here. What is perpendicular? Perpendicular is A. Okay. If this is phi, perpendicular is the angle opposite to that A. Hypotenuse is R. So it becomes A by R. Okay. This is sine phi. Now in this equation, let me put the value of dB. That is integration of dB is over here from equation 1. Mu naught by 4 pi I dl by R square, and sine phi is A by R. Okay, this is sine phi, that is A by R. Now, when we integrate this, we take all the constant values out of the integration. So what are the constant values over here? Mu naught by 4 pi is a constant. If you are taking this particular loop, radius will, this R, sorry, the distance from this point to the loop, from any point to the loop will still remain the same. So R is also a constant. So what changes only is the dl. Only dl factor is changing. The rest everything is constant. The rest everything can be taken out of the integration. So mu naught by 4 pi I dl divided by R square into R is cube. A is also constant, that is the radius. Integration over dl. Now integration of dl. What is dl? When we integrate all the dl, when we add up all the dl, what we get is, we get the circumference of this loop. So what is the circumference of the loop? Integration of dl is circumference of the loop. Formula for circumference of any loop is 2 pi r, that is the radius. R is the radius, so r over here is a. So circumference of the loop, or this integration part will be 2 pi a. Okay, that is circumference. Rest everything will be similar. So rest everything we can write it as it is. So we can write this as B is equals to mu naught by 4 pi I dla by R square R cube into 2 pi a. So this is the magnetic field. But let us make this more simpler. For that, first of all, let us find the value of R square. To replace this value of R, we'll see what we can write. Now R square is equals to, if this is a triangle, we apply Pythagoras theorem. R square is equals to base square by perpendicular square, that is a square plus x square, or R is equals to, if we remove the square, what we can write is root over here. In place of a root, we can write half to the power half. So in place of R, we can write this in this equation over here. So we will substitute that. So in place of B is equals to mu naught by 4 pi I dl. A into A will be A square 2 pi. Okay, before writing this, before doing this, let me cancel some of the things over here. 2 should be cancelled, pi will be cancelled. Okay, now we can reduce it further. B is equals to mu naught by 2 Only 2 is your ideal. A into A will be A square. Oh sorry, this DL we have substituted. I'm so sorry, this DL we have kept it inside, so DL factor will not be there. A square divided by R cube. Okay, divided by R cube. So in place of R we are writing A square plus X square cube. Half is also there, so this becomes 3 by 2. You can directly write 3 by 2 or you can write it 3 into 1 by 2. It's the same thing. Now, I think we can draw this diagram. Okay, now let us solve this part. So your B becomes mu naught I A square divided by 2 into A square plus X square 3 by 2. Suppose for n number of coils. If there are n number of coils, we multiply this equation by n. That is the number of coils. So your B becomes, if you multiply this, it becomes mu naught n I A square divided by 2A square plus X square 3 by 2. This is the equation for n number of coils. Now the last thing, that is for at the center of the coil. You can look at the diagram at the center of the coil. So when we find at the center, if we are considering this point P at the center of the coil, then this x becomes 0. So when x becomes 0 in that equation, what we can change is, in place of x, if it becomes 0, then remaining part is A square 3 by 2. So this 20 gets cancelled. So this becomes mu naught n I A square divided by 2A cube. And this can also be reduced like this. So your B ultimately becomes this will be the equation of B at the center of the loop. So this much for today. We'll continue in the next class. Thank you.